everyone. So today we will introduce a new topic, which is the principal component analysis, which is one of the reduction technique. In this technique, the algorithm will try to find out the maximum variability among between variables and try to compress it into a lower map, which is in this map we will have a variable, an orthogonal variables, and they will be representing the original ones. So the first step for you guys is to open a Jupyter notebook or any IDE that you find yourself comfortable to work with. Then we will start importing the libraries that we're gonna work with. So NumPy as a BD, and then we're gonna import the maths, the plot, lib dot by uh, plot as a PLT, and finally from sklearn dot decomposition, we're gonna import the PCA. Now, for the sake of experiment, so we're gonna generate a random samples where we make sure that there is a three variables have a very high correlation. I think I have made some typo here. So decomposition. Okay. Now let's basically fix our seed to anytime we run the data, we will get the same number. So nb random dot seed, and I will put my favorite number, which is 123. Now let's decide the size of this matrix. So and the numsam will be 1000, for example, and the variables that we're gonna play around will be 10. So number of variable equals to 10. Now let's start defining the first variable. So var1 equals, let's just assume this is a random variable. So nb dot random dot rand, and basically this command will generate a continuous uniform distribution between 0 and 1, and we're gonna put it at the size of the samples that we have, so numsam. Now let's fake the second variable, which will be a highly correlated to this one. So this is 2 by var1, and we will add some noise. So this is will be uh, nb dot random, but this time we want to make it Gaussian or normal distribution. So normal with a mean of 5 and standard deviation of 1, and also the same size. Now let's create also the third one. So var 3, and this time make it -3, for example, multiply by var 1 plus also a random noise, and make it random normally distributed. So normal with 3.5 as a mean, 0.75 as a standard deviation with number of sample. Now we have the remaining variables. So we will call this remaining vars, and this is will also equals, let's make it 1.5 multiplied by nb dot random, and also this is going to be rand uniform, and this is going to be for the number of samples, and also the number of variables num var, since we created three, so this is will be -1. Now let's combine them together. So this is going to be our data set here. So data equals nb dot uh, column underscore stack open two banana brackets, and this is going to be var1, var2, var3, and the remaining variables, so remaining vars. And we're gonna run it. I'm trying to check out what's the problem here. Says in var3. So let's go there. So it's minus 3.5 by random normal. Seems to me very close to the previous one. Okay. Okay. So this is comma instead of this one. Okay. So this is the problem for me. It was sensitive for this one. Now we will assume how many components. So we just will create the same number, which is the maximum here for the sake of a training. So no number of components will equals to 10. Now we're gonna also apply PCA. So PCA equals PCA for our data set here. So component or N for components is equals to also, this is the even it's a name here, so we will call it N components. I will try to make sure I don't have any typos here, so we will not have any mistakes. And now we're gonna fit on our data. So PCA dot fit to our data sets here. Okay, so we have applied. Now let's basically see how is the corresponding data set for this one. So we're gonna do what's so-called a secret plot. The secret plot will give you a visualization to see how much variability have been absorbed by each component. So PLT dot figure, so this is to show the figure size, fig size equals open another bracket between or banana bracket 10 and 6. And this is gonna be PLT dot plot. Now we're gonna plot a range. So range from 1, so open a banana bracket, to the n components. Now, because of the components will start from 0, so we're gonna always add 1. Okay, so this is the cause of that. Then after the closing the first banana bracket, we're gonna apply the PCA the explained variance and underscore, and this is going to be marker equals O, and we want to make the line style kind of dashed, so the line, or um, like a line style equals minus. Now let's see which is in the x-axis and the y-axis. So plt dot y label here will be the eigenvalues. So eigenvalues, and in the x-axis, so plt x label will be the components. So here the principal components. The grid also could be helpful. So plt dot grid, especially useful when you have data set are very close to each other. And finally, we want to show it. I make a typo here, so let's make sure I didn't do it. Now, this is also called a script plot and elbow. So it's also, we can add the title for that. Miss that thing here. So this is plt dot title script plot, and run it. Okay. So this is tells you the values of your eigenvalue. So we have the first eigenvalue, which is hold the highest variability. So it was 1.75. Now the second one also holds a great value. And then the third one coming to around 0.25. So that's give you a hint that if we're gonna select the number of represented components, so mostly we're gonna use 3, because 3 meaning this is where is our elbow, and this is like these numbers are contributing the highest. Now there is another way, which is through the cumulative one. So plt dot figure, and we're gonna use the figure size. Fig size equals to, let's do the same thing we done here before, so we can have a comparable graph. 10 and 6, and we will do the cumulative. So plt dot plot, and again we will use the same thing here. So we will have the range starting from 1 to the length of the cumulative variance ratio. And so because this is will start from 0, so we will always add 1 here. Now after that, we're gonna add a comma, and this is also we're gonna use again cumulative variance ratio, and This is the marker here. Marker equals O, and the line style is equal to minus. After that, we can also name it. So PLT dot title, which is the cumulative explained variance ratio. And so for the X label, PLT X label will give us the or the number of components, and PLT dot Y label will be a cumulative explained component, explained variance ratio. And let's add a grid. So PLT dot grid and make it true. And finally, we're gonna show it. Dot show. See here. So I have forget to define or basically determine the cumulative ratio. Okay, so let's me determine it first. So cumulative variance ratio will equals NB dot U sum PCA dot explained variance underscore ratio underscore. Another error. There is a typo for variance. Okay. Now, after doing that, you will see here also. So this is like how much we have explained. Now, like usually the people like to see the 80%. So you're gonna go with like 4 components in this scenario. So or with the elbow, when we see the elbow, so I can tell like in the elbow, but that's like controversial, meaning we are okay with the 64%. So it's up to you how much you want to recover. Usually 3 is good here, so it can explain more than 70. And it depends on the sensitivity of the problem, like how much you want to recover. Okay, in the class, we will talk about this thing, um, and we try to resolve the problem in other data sets.